Yeah, perfect. So yesterday we saw, right, the upper half basically samples the even samples, like gives us the even samples, and the lower half gives us the odd samples. So basically, uh, these are the odd samples, and these are the even samples. So we are dividing it by two channels. So this is channel 1 and this is channel 2. So in order, like for example, we have done this with channel 1. So now again parallelly we don't want to do this again with channel 2. So that's why we advance it by t, because we are discretizing it with a sample of t, right? So we will advance this by t, and that's when it will go to the next sample, basically give us the next sample. So then we advance it by time t. That's why at point d we have like same Fourier transform or same spectrum x of c, xc of f, but we have the advancement with t. So that's how it is represented: e to the power j omega t. This is omega 2 pi f. So again, uh, after d, like after point d, we sample it. So at point e, we have the sampling. So same equation, like same spectrum, but we have this factor as well, right, while sampling. So this factor adds up over here, and this complicated thing I have written on the next page as well. So the factor adds up here like this: e to the power 2 pi f minus k times fs times t. So this we discussed earlier. So what we have done is we have basically replaced 2 pi f. Now it's not t, it's 2t. So we have replaced 2 pi f 2t with omega. So we have basically scaled it, nothing else. And when we talk about the spectrum at point E over here, so this is upscaled by 2 at point F. So basically, this is what we get when we solve this, and when we upscale it, basically when we replace frequency by omega fs by 4 pi. So this is what we get. And then f we just upscale omega by 2 omega, and then we advance the signal by t, right? So again we have to take back when we add it. So we introduce a delay of t by introducing a 0. So we'll talk about it later on. So then at point G, so this is the upscaling, and then when we again introduce a delay, so when we advanced the signal, we had e to the power j omega t. Now we have e to the power minus j omega. So while doing it, so when we solve these e's, so we have addition of the this thing, powers. So basically we are left with this value times e to the power minus jk pi at point G. So what interesting is, so at point G and C, we have two samples, or two sampling modules, which we will add up in the end to get a single sampler, which looks like it is operating at frequency fs. So that's what we basically wanted, right? We wanted a sampling of fs. So we'll talk about it. So these 2 points are crucial, C and G. So
Yeah.
okay, then nice, perfect. So yeah, we talked about the full rate sampling, right? And we also talked about time interleaved sampling, and we analyzed the spectra at different points. So as I mentioned earlier also, so I was mentioning that when we consider the boundary condition, so we know that sampling frequency is 1 by t, and when we say that sampling frequency is 1 by t, thus the highest bandwidth according to Nyquist criterion, which is possible, is basically 1 by 2t. So now let's say the bandwidth is 1 by 2t. So then we will require a sampling rate which cannot be lesser than 1 by t. So when we look at the time interleaved sampling, the sampling is also happening at 1 by 2t, because we already said that 1 by t is too high, so we will use lower samplers. So then this is deviating the Nyquist, which is resulting in noise aliasing, because we know that if we deviate the Nyquist theorem, then noise will be aliased. So that means that in order to get no noise in the output, basically at H, so uh, there is something at this adder which makes the noise from the both ends cancel each other in order to get output with zero noise. So then we saw the spectrum mathematically from point C, so from this node and from this node. So for the point C and G, we have these spectra represented mathematically. So then we'll just talk about it. So when we had full sampler, so in the case of like sampling directly, where we scaled from 2 pi ft to omega, so we have this scaling table and we are aware about it. So basically when our sampling frequency is fs by 2, so that's the boundary condition, right? So that's where our um, bandwidth is, bandwidth lies basically. So if we say that we have a spectrum with bandwidth b, and this is basically fs by 2, so which is sampling frequency by 2, so then we scale it to this value. So then we considered that our sampling frequency is nothing but 1 by t. So then when we scale it and when we do the convolution of both, then this is what the spectrum will look like for our output. So we are familiar with this technique. So now in case of the time interleave sampling, we know that fs is not 1 by t, it's lesser than 1 by t, it's half of 1 by t, so it's 1 by 2t. So the scaling is only done by pi and it's not done by range of 2 pi. So first it was shifted by 2 pi. Now it will be only shifted by pi, and we know how. Like this is the reason. This is the scaling table. So if the scaling is only done by pi, so then the output spectrum will look somewhat like this. And we discussed in previous video that this will give us the information loss, or it will give us the noise aliasing. So then so basically in our time interleaved sampling, both of our channels, so this is our uh, channel 1, this is our channel 1, and this is our channel 2, and both channels will have somewhat of noise aliasing, and we need some sort of system which cancels out the noise at this node in order to get no noise at edge. So basically looking at the spectrum mathematically, and when we plot this spectra mathematically, so what happens is at node C, this is the operation which we are performing. We scale it, we convolute, so this is what we get. But at G, there is an inversion, as we see over here. So there is an inversion, and due to this inversion, instead of getting the convolution like this, or instead of getting the shift like this is inverted with the same shift. So when we call convolute, so after convolution, or after doing the operation, we get somewhat like this. So we have this from node C and we have this from node G. Basically, this talks about noise, and this also talks about noise aliasing. And hence, when we plot the spectra of adding up both the nodes, so basically we had this, then we shifted this with pi. So when we shift it at C, we get something like this. And at G, when we do the shifting is uh, in the inverse. So at G, we get this. And when we add both the nodes, so basically this effect is cancelled out, and we again are safe with our output spectra. So there is no noise. So these spectra or these things talk about noise, and that's how we cancel out the noise, even though if we are getting noise, and even though if we are deviating the Nyquist theorem, and we are having the noise arising, but the noise is getting cancelled anyhow. So we are again okay with it until and unless we are not getting the noise in our output spectra. So that's how it works, and that's how the technique is um, in a working condition. So then, until now, we consider that the sampling occurs simultaneously, right? But in reality, there might be some non-idealities, because uh, the sampling happening parallelly at a exact instance of time, or with exact amplitude, is somewhat very ideal to consider, because we are building two channels, right? So there are lots of factors which will affect the channels, and it will deviate and it will create non-idealities. So we'll talk about those non-idealities and how it affects this kind of system. So basically, the non-idealities are offset voltages or some gain factors. So we'll discuss about it. We'll start with offset voltage. So what is the offset voltage? So it is basically the error, uh, minute error, which is present when we do the difference between two nodes of, let's say, an op amp. So when we design operational amplifier, so when we have our integrator, so we take difference between the two input nodes. So while taking the difference between two input nodes, we always have some v offset. So that's the error which deviates from the actual difference, and that's the parameter of designing components. So every component, not every, but components do come with offset voltages, and due to those offset voltages, uh, non-idealities occur in our circuits. So we'll talk about that. So we have V offset over here. So initially, in ideal case, we had nothing, but now at this point, there also exists offset voltage from outside. So let's say we have V of 1 and V of 2. So you can refer to the playlist analog IC design for knowing better, to get to know more about V offsets. So yeah, so we will discuss the effects due to V offset. So we have our V offset along with our signal, which are coming through these two channels. So basically, we have a system, right? So we have a system, we have something input, we have something at output. So now v offset also adds something to the system, then we'll have also something minute at output, which is along with our desired output. So if we ground the input, for instance, so there is nothing in the input, so then at the output we'll only get the effect due to the v offsets. So that's what we are going to do. So when we ground the input, then we can analyze what actually we get at the output due to v offset. So then due to v offset, what will basically happen? So at the output we get the sampled signal, right? So the time is sampled, but along with that, whatever amplitude we have, so whatever voltage we have at the output, on the top of that, we will get some v off in addition. So we have our even samples, which are sampled by this channel, and this channel basically samples odd samples, right? So that's why we have represented this sampler with two kt and 2k plus 1t. So this is basically the representation of even and odd. So we will get our even samples, which will be having v of 1 in addition, and this is the v of 1, and we will be having v of 2 for this channel. So to represent this along with output spectra, so this can be represented by two things, not parallelly but at the same time. So our output will consist of these two things. So each channel is basically adding a fixed constant offset voltage to the output samples, right? So if we take these two values and we basically take the average of these two values, which is basically v of 1 plus v of 2 divided by 2. So it will lie something in between these two. So that's one parameter we will get along with our output samples. And we will also get a tone like this, whose peak to peak value will be v of 1 minus v of 2. So these two things, non-idealities, we will be getting along with our output sampled signal. So the non-idealities due to v offset causes extra offset DC voltage at the uh, output, which is this. So this is the extra offset DC voltage, and along with that, we have a tone, and this tone has a frequency of pi. So it has its samples, or it's repeating at pi, 2 pi, 3 pi, 4 pi. And when we talk about four samplers in parallel, so we talked about two, right? So what if we had four samplers in parallel? So think about it, like what can happen. So if we have four samplers in parallel, so then basically we will get this DC offset. Along with that, the tone due to the offset voltage will be at omegas, or the frequencies, which is pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, and so on. Basically, the Fn of that tone will be Fs by 4. But over here, in case of two samplers, it was Fs by 2. So the second non-ideality due to the gain error uh, is basically there exists a gain to the signal whenever we perform any operation in a system. So the non-ideality also occurs if the gains of all channels, basically in this case we have two channels, so the gains in these channels will not be same. So ideally we consider that the gain was same. That's why we were not deviating, or deviating from our outputs or the ideal outputs. But now, in reality, the gain, like we will also face a gain error, and that's why we will also face the non-idealities. So ideally, what we consider that, let's say there is a gain to our signal, and it is represented by 1 plus alpha and 1 plus beta. So initially, like ideally, when we saw this system, we considered no gain, or we considered 1 as the gain. So now, due to the gain factor, we have gain through channel 1 as 1 plus alpha, and through channel 2 we have 1 plus beta. And ideally it was same, so alpha was equals to beta, which was equals to 0. But now, due to random mismatch between both channels, so basically these channels are represented mathematically over here. But when we will design this channel, so we will be having mismatch between the components, even though we will use same components, but there is a mismatch between two components, even though if they are same. So I've talked about this in my other playlist, so you can refer to those videos. But yeah, so in reality, alpha will deviate from beta somewhat, and they both will not be equal to 0. So we have to consider what happens to our output due to this non-ideality. So let's say if alpha is basically equals to beta, then there is no real problem as such. We'll just get the output with some gain, but we'll get the output as desired. But when alpha is not equals to beta, let's say the gains over here are not equal anymore, and let's consider that alpha is greater than beta over here just for the sake of analyzing. So then we had this kind of uh, system, right? So for channel 1, basically from here the spectrum of point C was like this, right? And this value was 1 by 2t, but now it will be 1 by 2t times 1 plus alpha. So basically this is the gain, right? So what gain does? So gain increases the amplitude. So that's why the amplitude is no more 1 by 2t, but it's multiplied by 1 plus alpha. Initially it was multiplied by 1, so it was 1 by 2t. So this was from the this channel, and from this channel the spectrum was like this. So again, the amplitude was negative, but it was 1 by 2t times 1 plus alpha. So then when we add them at this point over here to in order to get the output, um, the noise parameters cancelled each other, right? So there was no aliasing. But now, as alpha is not equals to beta, so the gain is not same, so the amplitudes are not same. And as alpha is greater than beta, so this amplitude will be basically greater than this amplitude. So even though this amplitude cancels some part of this amplitude, but still a little part of this amplitude is still remaining in the output spectrum. So mathematically, if you want to represent, so this amplitude will be nothing but 1 by t plus 1 by 2t times alpha plus beta, because we are adding these two amplitudes. And as we are subtracting or removing the cancelling the effect, so this will be represented mathematically by 1 by 2t times alpha minus beta. So so that's how noise still remains if there is non-ideality. So we will talk about this non-ideality in further detail in our next video. But I think that's all for this video. So if you have any doubts, please let me know.
In my side, it's completely clear, but yes, I will ask some questions next, maybe tomorrow.
Okay. And Sneha, what about you?
Yeah, Rishi. So I wanted one clarification. So I understood that when alpha is not equal to beta,
Mm-hmm.
there might be the amplitude might be higher and it will not cancel out completely. So
Mm-hmm.
what about the actual output? So even does that get adds up, like not the noise?
Yeah, so this is the spectrum of our output, and the noise will get add up to the um, output spectrum, and we don't want noise. So but yeah, like again, we cannot design a system in ideal way. There will always exist non-idealities, and always there are efforts to reduce the non-idealities. But again, like achieving ideality is basically achieving infinity, but we can never reach infinity, right? So we will always go with non-idealities, and that's why like we always talk about the signal to noise ratio. So that ratio is given for your system. So when you design a system, you say that yeah, okay, fine, this system will work fine with this kind of signal to noise ratio. So basically, what is signal to noise ratio? So if noise was actually zero, so signal upon noise. So if noise was properly zero as ideal case, then signal would be at like the like reaching infinity, right? But that's not possible. So there always will exist a noise, and that's due to the reality of the components or non-ideality of the components. So that was your question, right?
Actually, no, but uh, okay, so we have these two waveforms, right? One is that 1 by 2t, 1 plus alpha, and 1 by 2t into 1 plus beta.
Yeah.
And we have the know that. output, the actual desired output which we need
Mm-hmm.
in both of the graph. So my question was, will those two get add up?
Oh, okay. I mean, these two.
Yeah,
Yeah, like
yeah,
these are just
yeah.
the harmonics, right? So we are only
Hmm,
interested in first harmonic. So it's basically it's
hmm.
second harmonic. So leave that. So every harmonic will get added. So that's why it is 1 by t. Like see, it's 1 by t. So initially it was 1 by 2t, right? So when we
Yeah,
add it, so it gets added to 1 by t. And that's what our sampling frequency is, 1 by t.
yeah, yeah. Got it, got it. Yeah.
Because when we analyze this for our simple like state system, so over here, right?
Hmm.
No, not over here. Over here. So this was
Hmm.
nothing but 1 by t. But then when we reduced our sampling rate to fs by 2, so then it got converted to 1 by 2t. And then when we like again add it, it goes to 1 by t.
Yeah, got it.
Yeah, perfect.